Welcome everyone. So the next talk will be obviously in English. One of my favorite TV shows when I was a child was Knight Rider. In France, it was called Academy. It was more fantasy than science fiction. I mean, ever heard about a male voice for AI meanwhile? And what if today, 43 years ago, after, we could build our own kit and with JavaScript? So please welcome Nico Martin with big applause.
All right. Hey, everyone. My name is Nico. And today I would like to take you on a little journey, of how I try to recreate maybe the most iconic car in television history right in the browser. But before we do that, I have two little things. First of all, I do have a lot of live demos in my slides, and yes, you are allowed to cheer and clap. And if you don't feel like clapping, I also built a little application. If you go to yay.nico.dev, you are able to launch a little firework in the slides. But I'm also able to, yeah, exactly. I'm also able to turn it off if you use it too often. But let's just see how that works. Okay, but who am I? So my name's Nico, as I said. Okay, it's already too loud. Let's keep it in the background. Yeah, my name is Nico. I am a machine learning engineer at Hugging Face. Hugging Face, for those of you who don't know Hugging Face, it's basically the hub for all about AI and machine learning. So you can host your models, you can host your data sets there on Hugging Face. We also have a whole tool set of open source technology that you can use for running your machine learning models, or all the things you can do with them. And I'm working on one of those, but I will get into the applications in the frameworks later on. And I'm also part of the Google Developer Experts program in both web technologies and also AI and machine learning, which means that I spend a lot of time in between the browser and this new cool AI space. Okay, let's start with a very simple question. Should start. Hello? Okay, who is K.I.T.? So K.I.T. is short for Knight Industries 2000. It's this advanced AI-powered car from this 1980s series Knight Rider. The whole series is pretty simple. It's this good guys versus bad guys, where Michael Knight tries to fight the bad guys. And then, of course, K.I.T. is this supercomputer. It's a car. It's a sophisticated AI. So it's very hard to define what is K.I.T. So maybe we should rephrase the question. What is happening with my clicker? Oh. What is K.I.T.? And in the 1980s, it was quite simple. Back then, K.I.T. was just a very advanced supercomputer doing very advanced supercomputer things. But then we learned about artificial neural networks. So maybe K.I.T. is just this huge artificial neural networks that learns by tweaking the connections between the neurons. But now we are in the age of AI. So maybe K.I.T. is just an AI agent that connects different services with a decision-making process. Okay, that makes sense. Let's build it. If we want to build it, we first need to look into the features. So what are the features that make K.I.T. human-like? First of all, it listens and it talks, so we can talk to it in natural language. It will talk back to us. It is intelligent, so it is able to process information, to act on that information. It has a personality. It's not just a soulless machine. It has humor, it has sarcasm, and all of that. It has a history, so Michael Knight and K.I.T., they lived through so many things together. We have episodes and episodes of stuff that they experienced together. So we have this huge action-packed history. And then last but not least, it has a body. So it lives in the physical world. It's not just a virtual application, it actually exists in the physical world. Now, if you want to build all of that, one thing is pretty clear: we need a lot of machine learning, a lot of AI. And I wanted to see if I can do everything in the browser. So the big question is, can we, or how can we use machine learning in the browser? Now, there are three things that we need. First of all, we need hardware, and we need access to the hardware. Then we need the frameworks to run the models, and on top of that, we need the models. Let's start with the first thing, hardware. So basically, machine learning is just a lot of little operations that run in some processing units. We can do that in JavaScript or in WebAssembly, which is then executed on the CPU. It works, but it's not very performant. If you want to have performant machine learning operations, we need to use the GPU. So there is a WebGL, which is this graphical abstraction layer on top of the GPU that then uses the GPU to run calculations. There's a new API called WebGPU, or it's rather new because it is available in Chrome since almost 2 years, I would say. But now it's also available in Firefox and in Safari Beta. So we are close to full browser support for WebGPU, and that is an API that allows us to run any kind of operations directly on the GPU. And then there's a new API called WebNN, because the problem is, yes, the GPU is a great unit to process machine learning operations, but some new devices they have, my phone, for example, has a TPU, the tensor processing unit. Some Windows laptops have a new NPU, the neural processing unit. And with WebNN, the idea is that we have one API that where then the operating system decides where it should run those machine learning operations. Could be on an NPU if they have, if the device has one. Could be on the GPU, or it could also be on the CPU. But that's only behind the flag in Chrome right now. Okay, so we have the hardware. Let's have a look at the libraries. And there's one library that I use quite a lot for building a kit, and that is Transformers.js. And that is also the library that I work on in my day job. So Transformers.js was released in 2021 by Joshua Lochner. He's better known by his handle Zenova. He then joined Hugging Face in 2023, so the whole project is now part of Hugging Face. And the idea of Transformers.js is to make it as easy as possible for you to use machine learning models directly in the browser. The way we do that is that we support around 155 popular model architectures across 27 tasks. So that also means we have close to 2,000 ready-to-use models that are on the Hugging Face hub that we can just add the ID to the pipeline, and we can then use them directly in the browser. The API looks quite easy, so most of it you can just do with a pipeline function. So we can import the pipeline from Transformers.js. We can then define a task, so what's the task that we want to achieve with that pipe. We can, if you want to define a model, so we can be very specific what model should be loaded. When this code runs, it will download the required files into the browser. That can take some time because some models are just a couple of kilobytes or megabytes, but some models, especially LLMs, they can be a couple of gigabytes, so we can use this progress callback to show the download progress. And then we can also decide whether we want to use WebGPU or CPU or WASM, and we can also define a D type, which is the compression that, or the quantization that we want to use for that model. So once we have the pipeline, we can basically take any input. The pipe will take that, it will run it through the model, and it will return the output. And of course, there are a lot of steps in between, but that's basically it. So based on the task that we define, also the type of the input and the output changes. Okay, so it's pretty easy to use machine learning models in the browser. Now let's see how we can use them to solve the first two problems. We wanted it to listen and to talk to us. So for the first part, we can use a model family called Whisper. Whisper was trained and open sourced by OpenAI. So we can use this automatic speech recognition task, We can then use the Whisper Tiny, and basically what we can then do is we can take the audio input from the microphone, wherever, we can then pass that through the transcriber, and we will get back the text. On the other end, we can use another model that's called Kokoro, and Kokoro.js was built by Joshua, so it's a very small abstraction layer on top of Transformers.js. What we can do here is we can use this tts.generate, where we can pass any input text. We can also define a voice, so there's a list of voices that Kokoro supports, and we will then get back the audio blob. Okay, let's have a look at the first example. So I have a little pipeline here that records what I say. It will transcribe that, it will synthesize it back to speech, and it will then output it from the speakers. Hey everyone, I'm here at Nantes at an amazing conference. It's so cool to be here.
Hey everyone, I'm here at Nantes at an amazing conference. It's so cool to be here.
Okay. So we basically have our end-to-end pipeline that takes the text as an input and returns text, or that returns speech as an output. The problem is now it's not really intelligent. There's one step missing. So how can we solve that step? The closest thing we have to intelligence right now is LLMs. So an LLM, I think we all heard of LLMs at this point, and we all use LLMs. But what does an LLM? Basically, we have an input text, roses are red, violets are, that runs through an LLM, a machine learning model, and it will then predict the next word. To be more precise, LLMs, they don't work with words, but with tokens and their token representation. So it splits up the input into different small token representations, and will then figure out the token that is most likely to be the next token. It will do that by basically figuring out the probability for each token to be the next token. So in that case, it's pretty clear it should be blue. And it will not always take the most probable token, because if it would do that, it would be it would generate very boring text. So there is also a little amount of randomness that we can add, and that is the temperature. So the higher the temperature, the more likely it is that it will take one of the lower ranked tokens. There's a great visualization by Andrew Bandera from the Google Chrome DevRel team. So here you can see we have the same text, roses are red, violets are, and then it will say, okay, that's 97% sure it should be blue. But if we increase the temperature, we can see that it will also more likely it will be more likely to take purple or violet, and that will then also affect all the other tokens that will be generated after that. Okay, so now that's basically what an LLM does in the end. Now there are quite a lot of LLMs out there right now. I think most of us use LLMs in this upper left corner. So there's GPT-4, GPT-5, Claude, Gemini, all those big models. And now the size of a model is determined by the amount of parameters, the amount of weights there are between the neurons. When we talk about GPT-4, there are estimated 1.76 trillion parameters. I think GPT-5 is more than 3 trillion parameters. And the problem here is, the bigger the model, the more processing power it requires to run those models. So for those models, we actually need to have specialized infrastructure that we can run them. But there are also small models like the Gemini Nano, which has only 3.25 billion parameters. And those models, they are small enough that we can actually run them on device, so on our phones or on our laptops. The thing is, those are closed models, so we are not allowed to use them in our own systems. But there are also open models. There are open weight models, and open weight means that the trained weights and also the architecture is open source, so we are allowed to use them. There's, for example, Meta with the Llama models. There's Google with the Gemma family, and also OpenAI with the GPT OSS, which is an open weights model family. And then there are open source models, and open source means that also the training data, so the whole training process is also available for us to see. So the whole pipeline is, in the end, open source. Then in that category, we also have smaller models. We have, for example, the Gemma 3 with only 270 million parameters. We have Liquid AI, we have Qwen. The Qwen 3 is a model that I've used heavily also for building K.I.T.T. And then we have open source models like the small LM3 from Hugging Face and the small version of the Apertus. Apertus, by the way, is a Swiss LLM, so it was a joint effort by some universities in Switzerland and the Alps supercomputer. So it's an open source LLM that was released about a month, 2 months ago, and yeah, all the training data is open source available. Now, there are way more models than just that. So all the models, or most of the open source models, are on Hugging Face. So if you go to the Hugging Face hub, you can see the text generation task. And there you can see that we have around 286,000 LLMs that are here on the hub that you can use. Again, those are not all single models. Also, that you have model variations, but there's just a huge variety of models available right now. Okay, so we now have models that we are allowed to use in our own systems. We know they are small enough that they could run on device. How can we run them in the browser? We can do that using Transformers.js. So there's this task text generation. I wanted to use the Gemma 3 270 million parameter model. And then I just have an array of messages. I have a system prompt and I have a user prompt. And I can then wait for the full answer. So if you have a look at an example, you are a helpful assistant. And then we have the question, who are you? And then we can click generate. It thinks for a moment, and it will then return the answer. Now, this is actually happening quite fast. So we can see that it is able to generate around 54 tokens per second. But it feels a little bit slow because we actually wait for the whole answer to be generated before we show anything. But we can solve that with streaming. So from Transformers.js, we can also import this text streamer. Now, this text streamer has a callback function, and this callback function will be called whenever a new token is generated. So if I now take another example here, you are a helpful assistant, but now I ask it to write a poem about the DevFest in Nantes. Problem poems can be quite long, so if I try that with streaming, we can see that it's actually quite fast. So we are still at around 55 tokens per second, but it feels super fast because it will just generate tokens as, or it will output tokens as they are generated. Okay, so let's add that to our pipeline. I now have the same pipeline as before, but now I have this processing step. And I can now say, hey there, I am right now at DevFest in Nantes. It's an amazing conference, and we are on stage right now. So could you quickly introduce yourself to the audience?
Hello everyone at DevFest in Nantes. I'm Gemma, an AI model developed by Google DeepMind. I'm here to help and chat with you. I can answer questions, share knowledge, and even help you find information. I'm excited to be here with all of you at this amazing conference. Let me know if you need anything.
Okay, so that did work, and we now have a full end-to-end pipeline, all happening directly in the browser. No calls to any servers are being made. But the thing is, we just created another random chatbot. Because now we're talking to Gemma, the AI model from Google, which is fine, but I wanted to talk to K.I.T.T, the sophisticated AI from Knight Rider. So how could I now personalize this whole experience? There's one way I could do that is I could use fine-tuning. Fine-tuning means that I take a model that is already trained, and I could then add more data on top of that to tweak the model in a certain direction. And to be honest, that is probably as hard as it sounds, so I didn't want it to go that route, but there is a way simpler way to do that, and a yet very effective way in the end, and that is basically prompt engineering. So prompt engineering is the process of crafting precise and effective input prompts to optimize the output of AI models. That means we can now just add another system prompt. Same pipeline as before, but now I tell it, hey, you are Kit from Knight Rider, you are a speaking car that talks with Nico, so I give it some context. And then I have a summary of Kit's tone, so it should be polite and formal, witty and playful, blah, 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 blah. And I can also give some guardrails. I can say, hey, I don't want you to output special characters, symbols like asterisks or similar, so I can be very precise on what I wanted to do and what I wanted not to do. So let's try the exact same pipeline as before, but with a different system prompt. Hey there, we are right now at DevFest in Nantes. It's an amazing conference, and we are on stage right now. So could you quickly introduce yourself to the audience? Okay, wow. I really hope it's generating a lot of tokens, because otherwise it just crashed. Doesn't look too bad. You know what? I will just reload the page and try it again. Hey there, we are right now at DevFest in Nantes. It's an amazing conference, and we are on stage right now, so could you quickly introduce yourself to the audience? Fingers crossed. Yes.
Nico, I see you're at the Deathless Be Nanda conference. The island stage is a fine place for a performance. I'd be happy to join you for 15 minutes with the audience. Just let me know when you're ready to take the stage. I'll be there, ready to shine.
Okay. So, it actually, thank you. That was the exact same model as before, but now the output was so different just because we tweaked the system prompt a little bit. Now, let's talk about memories. So the thing is, I wanted to, as I said before, there are so many things that happened in the past, and I wanted to be able to talk to Kit about things that happened in the Knight Rider episodes. So the next couple of slides, they took me quite some time, but I'll try to make it as short as possible. So if you ever find yourself in the same situation where you want to basically create a database of your favorite show, first step, you might want to go to Reddit. There you will find a subreddit of your favorite show, and I'm sure you will find someone who has a link to a website that has all the screenplays of that show. Then you can write a little playwright script that scrapes all the screenplays into plain text. Then you will figure out that those screenplays are written in pre-World Wide Web time, so you need to write your own little parser that takes this structure and parses that into a structured JSON. And now you're done. You have your 6,275 scenes in 432 acts in 84 episodes that you can put into your database. In my case, I wanted to have them in the IndexedDB. Problem is now that I have a question about a series, how does Bernie Mitchell present himself in season 2? And then I have a lot of scenes, a lot of acts. So how can I build a little robot, a little function that knows what scene I'm referring to? Back to my IndexedDB. IndexedDB is a document database, so I have a structure of all the scenes with the text, and I could now use words to then figure out, okay, I have those words in the questions, or maybe I need to find the same words in the text. That could work, but it's not not a very good approach. A better way to do that is to use a vector database. Problem is, IndexedDB is not a vector database per se, but basically everything can be a vector database if you have the thing that you want to store and a vector representation. Now, a vector representation is nothing more than just an array of numbers, and those numbers represent the position of that thing in a specific vector in a multidimensional vector space. We can create embeddings with transformers.js. So we have this pipeline function, and then we can use the feature extraction task. I'm using the all-mini LM L6v2 model. And there we can just pass some text through the disk structure, and it will return this array of 384 numbers that represent my text. The other problem, that's the example. So we can see that we have a source, hello people from France, and then we have another source, good afternoon developers from Nantes. As you can see, there are no shared words in that, but we have the vector representation for both of those sentences, and we can calculate a cosine similarity score, and that is basically the idea of how close are those two words together in this multidimensional vector space. So if I change that from Nantes to London, you can see that the similarity dropped because we still have a lot of shared or a lot of similar words, but France and Nantes is closer together than France and London, and that's why now the similarity is lower than it was before. Okay. Now we have this whole scene, and the problem is some scenes, they are super long, they have multiple conversations with multiple people, and some scenes are super, super short. So how can we now generate small summaries in the end that we can then use for vector search? My solution to that was to use this LLM summarizer. So the LLM summarizer is nothing but just a function that takes the text as an input. It will then estimate how many plots I can expect. So the longer the text, the more plots, the more summaries I would expect. I then have a system prompt that is very, very short. And I have a user prompt where I tell it, hey, this is a scene from the TV series Knight Rider. Find the main plot lines, summaries, a maximum of max plots. And then I'm also very strict about the output format. So I tell it it should return a JSON with all the summary, or a JSON array with all the summaries as strings. Make sure it's valid JSON. It's very important to put that in. It doesn't work all the time, but for most of the time it did work. And you can also set the temperature to 0 because I don't want the model to find crazy new ways to generate JSON structures. I want it to have some parentheses when they have to be where they have to be. And yeah, that's basically how I summarized my 6,275 scenes. And my poor little MacBook had to process 3.1 million input tokens to then generate 303,000 output tokens. It kind of did that. It took a couple of days. It also crashed sometimes, but I was able to do that on my laptop. And now I have a database that looks like this. So I have the text, then I have an array of summaries, and then I have, for each summary, its vector embedding. That also allowed me to create a vector search function. So this vector search function takes the query, the question. It will then create the embedding for that question. It will then open the IndexedDB. It will get all the scenes. It will then go through all the scenes, and it will then find the 4 scenes that have the highest similarity between the scene or between the summary and the query, and it will then return those scenes. Okay, now I have a function that finds those scenes, but the real question is, how can I use that function in my agentic workflow? We can use a concept called tool calling. A couple of things about tool calling. An LLM cannot execute a tool or a function, but the application around it can. The LLM can detect when it should call a tool, and based on the input, it can then generate structured output. It could be just some text, it could be an XML, or it could be JSON. And the application can then take that, it can execute the function, it can return the output to the conversation, and the LLM can then process that in the next step. The way that could work is like that. So we have this little system prompt, and in the system prompt, I tell it, hey, You have tools that you can use. You have the tool find memories with a description. You have the parameters that you can use with that tool. And then, and that's the important part, I have examples. So I give the LLM examples on how it can, or in which situations it should call this tool. And then I'm very strict because I expect it to create a little XML snippet with the tool name and the parameters. And there we go. If I now click generate, it should now generate this tool call, find memories, and I could now take that. But the cool thing is, if I have a question that it can just answer right away, it will do that. So I can now ask, who are you? And as you can see, it now should not generate a function call, so now it will just generate the text. As you can see, I'm also using the Qwen 3 LLM here, not the Gemma. And I did a lot of testing, and I figured out that the Qwen 3 4B is a little bit slower. It's bigger, but it works way better for generating structured output. OK. The thing we just created is called RAG, which stands for Retrieval-Augmented Generation. And the idea is that we have a question, but before it goes to the LLM, it will retrieve more context. It will augment the prompt with more context, and then it will generate the question based on the generate the answer based on the question with all the context that it just retrieved. To be more precise, it's agentic RAG because the application in the end decides if it needs to retrieve information, and sometimes it doesn't need to retrieve information. And to have the whole buzzwords in one place, that is basically also an AI agent. It's just a program that autonomously completes tasks or makes decisions based on data. OK, let's try. So I have K.I.T.T here in the browser on kit.nico.dev. I can now wake it up. And I can then press the space bar to communicate. Come on. There we go. Good morning, K.I.T.T. How are you?
I need to find the information about the car that hurt me in Season 5. Let me look it up.
Wait, what? But the cool thing is, I also have this log here. Let me just reload that for. Those are the best moments when giving a talk, if things don't go as planned, but let's try. Good morning, K.I.T.T. How are you today?
I am well, Nico. How can I assist you today?
Do you remember the connection between Sony and the deadly poison gas exchange, and did something tragic happen back then?
I am recalling the events from the past. Let me look up the specific episode to provide you with the details. I see. It seems the events you are referring to are from Season 3, Episode 8. The connection between Sony and the deadly poison gas exchange is not directly mentioned in the episode, but the events do involve a deadly poison gas exchange between Sonny and Fidel. A canister of poison gas is accidentally discharged, killing a bystander, Laurie. Michael is left devastated and helpless as K.I.T.T confirms Laurie's death. The episode also includes a scene where Michael and K.I.T.T are surveilling Birok and Zormagian, who are illegally disposing of hazardous waste and planning to burn the evidence. Michael uses K.I.T.'s
Thank you. Yeah. LLMs are non-deterministic, so you never know how much and what it will produce, but it's not that bad. So what we see here is that we have a system prompt, and the system prompt is quite big. I have all the things that you've seen before, so all the summary about K.I.T.'s tone. I have all the tool calling stuff, so I have the search episode tool. I also tell it how to call a tool, so that's basically all we've seen in this talk so far. Then I have my question, and here it will generate, I am well, Nico, can I access you today? That's fine, it did not have to call a tool. Then I had my second question, do you remember the connection between Sony? Mm-hmm. And then it was like, okay, let me think of that. I need to call this tool. Now my application can now parse that, and I'm using XAML because it's just easier to parse for me in the application. So it parses that, it says, oh, I need to call the search episode tool with this question. I will then, or the application will then call that tool. It will then return the results into the conversation as a tool call or a function call result. And now K.I.T.T is able to generate a new answer based on the question I had previously and all the context that it had from the show. OK, now I have K.I.T.T working in the browser, but there's one thing missing. I wanted it to have a body. Now, I did look at some Pontiac Firebird. Turns out they're quite expensive, and 20,000 Swiss francs is not exactly what I have in my side project budget. And also, I am not a mechanic, so I had no idea how to deal with a real car. But I'm still a kid at heart, and so I was able to create a little Lego kit that I was able to build. And the problem is now that I have this little car, this kit, and I have my web application. And how can I now communicate with or how can my web application now communicate with the car? We can do that with Bluetooth. There's an API called WebBluetooth that allows us to communicate with BLE devices around us. So the way Bluetooth works is pretty simple. We have a so-called generic attribute profile that has a K.I.T.T server. The server contains a list of services. Each service has a list of characteristics, and then each characteristic defines what operations can be performed on a value. So I can, for example, read a value. I can sometimes write a value, and I can also be notified when a value changes. And then we have K.I.T.T values, and those are just arrays of bytes. So if you look at this example here, that's an example where I could connect to a little light bulb. Here I need to first get the device. So I have the navigator.bluetooth.request device, where I filter for all the devices with a specific name. I can then connect to the server. Once I have the server, I can connect to the light service, to the characteristic, and I can then read the values from the characteristic, and I can also write new values on that characteristic. And then I also have my car. And my car is basically just an Arduino Nano RP2040. It's a very small Arduino microcontroller chip that is connected to this LED strip, and it's also connected to the motor controls and to the batteries. And on the Arduino, I have a small C++ script that exposes one BLE server with one service, one characteristic, and that characteristic has 2 bytes. I have 1 byte that controls the left side of the car, and 1 byte that controls the right side of the car. So I can, if I set it to 0, it would go full speed backwards. If I set it to 200, it would go full speed forward, and everything in between. On the other side, I then use the WebBluetooth API to connect to the service, to the characteristic. And then I'm able to get the current speed, and I'm also able to change the speed for the left and for the right-hand side. OK, let's get back to the application and try it out. So if I now turn it on, it should, beautiful, it should tell me that it is able to connect. And I can then connect to the car, and there we go. And I can now use arrow keys to control the car. So that's all happening by just using arrow keys. That is cool, and I have 10 minutes left. I could now ride the car for the next 10 minutes, but what I wanted to do is I wanted to use that thing in the whole agentic context. So let's see how that works. Hey, K.I.T.T, we have a problem. I think we need to get out of here as quickly as possible. Can you go full speed forward?
Out of here as quickly as possible. Let me check the road conditions to ensure it is safe. I am going to need to make a decision on the best route to take. I will be monitoring the surroundings for...
Yes, thank you. So as you can see, it now took the input and it decided that it is best to just go full speed forward. Thing is, I said full speed forward, and I could do that with just pattern matching, where when I say full speed forward, it would do full speed forward. But what I have here is not just pattern matching. I have actually an LLM that can actually reason about the request that I had, so it can also do more complicated stuff. So if I, for example, say, hey kid, we have a problem. There's a roadblock in front of us, and on the right-hand side there's a river, so we can't go right either. What should we do next?
I am going to make a left turn to avoid the roadblock and get us out of this situation. Let me check the road conditions to ensure it is safe. I am going to need to make a decision on the best route.
I don't know. Sometimes when it is in this mode where it just will generate answers and like generate a lot of text, it will continue to generate a lot of text. Most of the times it will just say what it wants to do and it's good. So I don't know why it's so chatty today. Never mind. OK, so we actually have K.I.T.T running in the browser. It listens and it talks using Whisper and Kokoro with Transformers.js. It is intelligent, kind of intelligent, using the Qwen 3.4b LLM. It has a personality using just prompt engineering. It has a history using all the scenes from Knight Rider and Agentic RAG. And it has a body using WebBluetooth and tool calling. So we now know what I've built. We now know how I've built it. The big question is, why? Why did I spend hours and evenings and weekends trying to recreate a car from a TV show that I didn't even watch when I was a kid? And the answer is pretty simple. Because I can and because it's fun. I started developing websites not because I had to, not because I was paid to do it. I was maybe 13, 14 years back then. I started developing websites because it was fun to see what is possible in the browser. We have HTML, we have CSS, we have JavaScript. We have so many APIs that are just there in the browser, and we can use them. The toolbox is huge. Now, with LLMs, we have one more tool. We have one more tool in our toolbox that helps us to build cool things. And that being said, thank you so much for your attention. My slides are there on the left-hand side. The feedback form is there as well. Thank you.